with increased number of transistors on a chip, many new ideas could be realized. And as we know it now, the machines which are the most popular and dominating the parallel programming is shared memory multiprocessors with coherent caches, such as your phone or desktop or any server. And essentially they are the Burroughs machine from 1962 with added cache memories. That's not a trivial feature to add. Well, it is, but the program will not work unless some other things are added as well. But we will come back to that. So it's relatively easy to invent new and faster parallel machines, but only if you can ignore the constraint of having happy paying commercial customers. Up to the end of the Cold War, I mean when the Soviet Union collapsed, it was the US Department of Defense which provided most of the resources for this new architecture. Okay, but how can a computer company put itself into bankrupt? Well, we will see a short list here. Namely, insufficient performance. First of all, spend a lot of money, which is typically what hardware companies do when they develop a new machine. And if it's not good enough, then it's wasted money. Or require, I mean, if it has good performance, but a new programming language is required, so the customers have to rewrite their algorithms, then it's not so easy to sell it. Or require non-standard extensions to C or Fortran. Also a bad idea. Customers don't want to be locked in to one vendor's compiler extensions. They want standard languages and be able to compile it on a different machine when that is needed. Okay, or simply taking too long time to reach the market, so it's obsolete before it's on sale. Okay, so new programming languages are of course not always bad, but it's difficult to create a new programming language and new hardware and succeed in the market. There was an effort in Sweden to, let me see, it was in the early 1990s when the project was cancelled. It was a big project and by leading Swedish industry that provided funding for this, but it required a new programming language, and it after a while those who owned this, who put money into this decided that it was just a waste of resources, so they cancelled it. Okay, so examples of parallel architectures. Massively parallel machines. We will come to that. Actually, we will come to all of this, but short description is that it's thousands of compute nodes, and they are communicating with compiler written messages. Okay, data flow machines. So MPPs, they are still around. Data flow machines, they are not around. not successful. Systolic arrays, not successful. This multiprocessor created at CMU. It is the foundation of the Stanford Dash, led by Anup Gupta. Okay, and multi-threaded machines, in the sense of this machine and a later company created by Burton Smith, is not around either, but there are ways to exploit multi-threaded architectures in the form of simultaneous multi-threading. But we will see what the idea about these machines were. Well, basically it was, you can, with Burton Smith's Terra machine, it was to skip cache memories and have multiple hardware threads running and letting one run for each clock cycle, so that if you have sufficient number of hardware threads, the memory latency can be hidden. But, well, we will see. They don't exist any longer. I mean, their architecture. Some form of their company may still be around, but not with that architecture. The Stanford Dash, that's basically the center of doing the research which resulted in today's shared memory multiprocessors. KSR1, that's and DDM, these are two very interesting architectures, but they are not around. KSR, Kendall Square Research, it was a commercial company, and DDM is a Swedish project, which is very interesting, and I will come to that. So, MPP machines. They have thousands of CPUs, and each node has a CPU and private memory, and programmers create messages, and a popular interface API is MPI, the message passing interface, and they are very much actively used also today.